Hello students, good evening all. So welcome back to our sessions. So today this will be our fourth session of chapter Indefinite Integrals. So we had already completed three where we are actually started discussing our methods of integration. So we are going to continue that. So we'll just quickly have an overview of basically what types of methods like methods of integrations which we have covered in our previous sessions, and what are the things we are going to cover in particular of our today's session of indefinite integrals. So coming to the methods of integration, so the first thing of methods of integration which we have learned is nothing but our substitution. So that we have already finished, and after the substitution the next method of integration which we have covered is integration by parts. Right, so we have actually followed the rule, that is UV rule of integration. Right, so I have mentioned here, instead of taking as U and V, we are going to give it as the easiest name, first function and second function, so that in a flow we can remember our UV rule of integration. Right, so this is our second method which we have learned, integration by parts. And in that integration by parts, we have seen some particular forms of functions. So for those we can directly have our integration. So one particular form is related to our exponential function, and one particular form is related to our logarithmic function, so which we have already seen that. Right, so coming to our today's session, the next method of integration which we are going to learn here is integration of rational functions. So you know what actually a rational functions are, right? So you have learned that in your functions chapter, so there is nothing new. But when it comes to the integration, how we are going to integrate this rational functions, right? Because if we follow in our general methods like normal integration or any of our by parts and all, it actually makes the rational function a bit complicated while doing the integration, because rational function is nothing but in a fraction we'll be having our polynomial functions, isn't it? So it actually makes the thing complicated when we normally do our regular methods. So that's why for our rational functions we'll be having a particular thing, so that we are going to learn in our today's session. So integration of rational functions. And similarly for irrational functions also, there is a separate way of solving that. Right, so however, how we will be having our integration for rational functions, similarly we will be having for integration of irrational functions. Right, so along with that we will be having irrational algebraic function also. So based upon the type of functions, the methodology or the procedure which we follow to do the integration will be varying here. Right, so that's why we actually having the methods will be added one by one based upon the types of functions which we are dealing here. So first we started with the rational functions. So for rational functions there will be a separate methodology, and for irrational one methodology, again algebraic function one methodology. But there will be a slight common thing that we'll be seeing when we are dealing with each of them. But in and overall, what and all functions we are going to deal here in our today's session, I'm just putting it here. So rational functions, irrational functions and algebraic functions. And at last, the same thing, even for our functions also we could have some standard integrals, so that it will makes our procedure a bit easy, a step ahead. Right, so that's the major reason for applying our standard integrals and all. So again here we are going to look into the standard integrals. Right, so in today's session, we are mostly focusing on rational functions and irrational functions. So let's see how it goes, and along with that, we are doing questions related to each of the type of functions. So before starting with the rational functions, here we are having some special integrals. So let's have a look in this special integrals, and then we'll just get back to our integration of rational functions. Right. So here it's like we can say it's a special integrals, we can say integration of some particular forms of functions, so anything. Right, so if we are having an integral of form integration of e power ax into sine bx. So this is my function here, e power ax into sine bx. So then directly my integration will be, integration of this function will be equal to e power ax by a square plus b square, the whole into a sine bx minus b cos bx. Right. Similarly here, for cos also we are having a formula, e power ax cos bx dx. Right. So it's like some standard special integrals here. So you can remember them as it is a formulas or else a standard integrals, so that they'll make our solving the question a bit easy, a step ahead. So that's the major idea of this special integrals or some standard integrals, those and all. Right. So guys, let's solve a question first and then we'll just get into our rational integrals. Right. So quickly, so far we have dealt with few methods. So you can just quickly look into this question. So this is a JEE level question. So that's why I just given you here. So we'll just solve this question and then we'll get into our integration of rational functions. So can you guys quickly solve this and let me know what's the answer for this? So you can use your substitution method also, no issue, it's up to you. So even just now we have seen our special integrals. So it's basically the application of it. So by looking at the given function, what can we substitute? Because here we are having exponential as well as our inverse trigonometric functions. So the first thing that should come into our mind is we can assume this given sine inverse x to be a t. So that will be my substitution here. So if I have assumed my sine inverse x to be t, then you can differentiate this one and you can substitute and simplify whatever the given function. And you will be getting the reduced form of our given function, that is given integral form. So quickly do that, guys. So I hope you have started with this by taking sine inverse x equal to t. That will be our substitution. So anyone got this one, please let me know. So if I have substituted my sine inverse x to be t, so what will be my differentiation here? So sine inverse x here. So from here, this can be written as x is equal to sine t. Yes or no? So my differentiation now will be dx will be equal to sine t, differentiation will be cos t, and here dt. So now if we substitute, what will be my given integral will be turning out to be? So e power t, and in place of dx, I can substitute cos t dt. So this is my reduced form of my integral after the substitution, that is in place of sine inverse x, I have substituted t. Right. So if you compare this, so just now we have seen our special integrals. Right, so this is something related to our, this one where I am having e power t, something t is equal to ax and cos bx. Right, so we can apply that particular formula here, our special integrals, and we can simply find the answer. So this will be e power whatever t, that divided by 2 into my sin t plus cos t, and constant will be as it is. So now in place of t, what we have to substitute? We have to substitute our sin inverse x. So e power sin inverse x by 2, and here sin of sin inverse x. So this will become x, and here cos of sin inverse x. So we can reduce this. So here this term will become x, and here sin inverse x can be turned out to be cos. So where this will become cos of cos inverse 1 minus x square according to our right angle triangle. Yes or no? So now my integral form will be equal to e power sin inverse x by 2. Right, the whole, because sin of sin inverse will be getting cancelled and it will be remaining with x here, x alone, and here the sin inverse we have converted into our cos using the right angle triangle, which it is turned out to be cos of cos inverse 1 minus x square under root. So cos of cos inverse will be getting cancelled according to our inverse trigonometric identities which we have learnt. So here we are remaining with root over 1 minus x square and the whole plus c constant. Right, so this will be my integral. So here there is nothing new we have done. We have just substituted in place of sin inverse x, we have substituted t, and then we just ended up having this format. Right, so that is e power something. Right, so here I am having e power something into cos of something dt. Right, so e power some t and cos of t. Then my formula here will be the e power t by 2, and whatever the angle here, that is sin t plus cos t plus c. Here I will be having some a and b. So you can just compare with the formula which we have learned, and this will be my result here. So the only funda we should remember is here what we are going to substitute and what's our special integral formula, and further we should only require the simplification. So that's it. So now let's get into our most important thing, that is our integration of rational functions. Right. So here for this integration of rational functions, we actually have some different cases. Right. So we'll start the cases one by one and we'll be solving one by one. So here comes the first case. So basically what is our rational numbers? Rational numbers are nothing but they'll be expressed in the form of fraction, that is in form of f of x by g of x, where both my f of x and g of x will be some polynomials. Yes or no? So you can see my rational functions will be expressed in this form of f of x by g of x, where both are polynomials. Right. So here comes my denominator g of x. So with that I will be having my first case of integration of rational functions, that is when the denominator can be factorized. So what is my first case here? When the denominator of given rational function can be factorized. Right. So here if the degree of f of x is greater than degree of g of x, then first divide f of x by g of x till the degree of remains. So we know the division, basically division of polynomials. Right. So when our denominator can be factorized, we will be just using our basic division of polynomials, and then we'll be writing that such a way that q of x plus r of x by g of x, where q of x is the quotient and r of x is the remainder and g of x will be our given dividend. Right. So for that we actually have some what we can say subsections inside our rational functions in our first case. So firstly, what is our first case? When our denominator of a rational function can be factorized. So if I am having, for suppose I am having a function such a way that 1 by x minus a into x minus b. That means here what, it is not necessary that the given integral should be exactly in this form. But if I can factorize my denominator, I can actually write it in this way. It's nothing but a simple factorization of a given polynomial. Yes or no? So whatever the given denominator of the rational function, if we could able to factorize that as for our first case, if we could write that in this manner, that is 1 by x minus a into x minus b, then how can we solve this? So we'll be solving this by equating it to a by x minus a plus b by x minus b, where capital A and capital B are real numbers. So now the question is, how we'll be finding this capital A and capital B? So we are going to find this capital A and capital B by equating this, right? So we'll simply cross multiply here. We try and solve this. We'll simplify this, and by comparing the coefficients of both sides of RHS and LHS, we are trying to figure out the values of our capital A and capital B here. So which are nothing but belongs to our real numbers. If once we are getting our A and B values, we can substitute that here and we can convert our this typical type of integral form into this form, and we can easily do the integration further according to our whatever methodology which we want to update. Right, so this is my first step, first type, when my denominator of a rational function can be factorized. So let's get into the second type. So this is my second type, when my denominator of rational functions can be factorized. So here if you observe, I am actually having same factor repeating. Right, so here what is my second condition? Repeated linear factor in the denominator. So whenever I can factorize my denominator, and when I factorize, if I end up having a repeated linear factor in the denominator, then how can I rewrite my function? Then that will be equal to a by x minus a plus b by x minus a whole square plus c by x minus a whole cube plus d by x minus b. So this is the way how we actually rewrite our given rational function. And as usual, so the way of finding our capital A, B and C is the same thing. So we'll be taking the LCM and we'll be doing the simplification, and then we'll just compare the coefficients of both sides of the given equation, and we end up having our A, B and C, D values. So if we have our capital A, B and C, D values, we can substitute it and we can just integrate it according to our requirement. Right, so this will be my second case. So basically in the rational functions, we are actually in the first case where we are talking about when the denominator of a rational function can be factorized. In that we actually cover two parts. The first part is when we are having a non-repeated linear factor. So here there is no repetition of the linear factor. And the second one, when we are having a linear factor which is repeating. So here my linear factor x minus a is actually repeating here. So this is my next case. And we are having one more case here. Right. So that is for every non-repeated quadratic factor in the denominator. Right. So here, so this is non-repeated, but it's a quadratic factor. So it's not a linear factor. Right. So even if we have a quadratic factor in the denominator, then also we can actually simplify our rational function. So that is my next case here, which we are going to deal here. So if I am having an integral in such a way that 1 by ax square plus bx plus c the whole into x minus d. That means here in my denominator I am having a non-repeated quadratic factor. So here you can observe it is a quadratic factor and it is not repeating. Right. So then what I will be taking here to my LHS, I will be rewriting the given rational function such a way that ax plus b by the quadratic factor, that is ax square plus bx plus c plus capital C by our linear factor x minus d. So as we are taking here the quadratic factor, the numerator will be having two variables, that is a, as well as with the two real numbers, that is a and b. So this will be my expression when I am having my denominator with a non-repeated quadratic factor in the rational functions, right? So here there is nothing new again for finding our ABC value. Same procedure, by comparing the coefficients of both sides of the equation, we end up having our ABC values, right? So let's get into our last case when we could actually factorize our denominator. So here I am having a repeated quadratic factor, right? So when I have my repeated quadratic factor, how will I be rewriting this? So this can be rewritten so as our similar way. So how we have written when we are having our repeated linear factor, right? So we have to combine our second and third case which we have discussed earlier, and we can combinedly write it here to express our next denominator where our repetitive quadratic factors appears in the denominator. So here what is my expression of the LHS? It is 1 by ax square plus bx plus c whole square, which means this is a quadratic factor but it's repeating, right? So this is my repeated quadratic factor and this is my non-repeated linear factor. So this whole given function can be expressed as ax plus b by ax square plus bx plus c whole square, okay, plus cx plus d, because we are again taking the quadratic factor in the denominator. So the numerator should be in the form of cx plus d. So cx plus d by ax square plus bx plus c, plus we are remaining with the linear factor here, non-repetitive. So plus another constant e by x minus d. So this will be my expression. So it is rare that we end up getting questions related to our case work, but we should be aware of when, if in case we are getting this form of integral also, we should aware that how should be solving that, right? So these are our 4 typical cases of our first type of rational functions, right? So what is our first type of integration of rational functions? When the denominator can be factorized. So this is our first case. So first type. So in this first type of our rational functions, we have discussed 4 cases. So what is our first case? Non-repetitive linear factor, right? Second case, repeating linear factor, and third case, non-repetitive quadratic factor, and fourth case, repeative quadratic factor. So these are our 4 cases which we have discussed in our first type of integration of rational functions. So let's try and apply this and solve one question related to our integration of rational functions. So you can just give it a thought first thing and then I can explain you this one so that we can do with the second question by your own. So just first take few minutes and try to understand the question, try to factorize it. So first thing is we have to check. We directly know that by looking at the integral, we know that it's a rational function which is given here. So now the second step is we have to check whether we could able to factorize the denominator or not. If we could factorize, what will be the factor? So that will be our first and foremost step here to solve this question. So let's do that. So let's factorize this given question, guys. The denominator. So if anyone factorize the given denominator, you can let me know. So what will be the given factors of this linear rational function? Come on guys, quickly let me know. So those and all who have factorized this given denominator of rational function, please let me know at least the factors so that we can proceed further, because it's easy. You guys already know how to factorize a given quadratic equation. Okay, Shivaranjani has already given the factors, guys. That is x plus 1 and x minus 2. Okay, correct. So let's see the factors first. So what is our given denominator? This is x square minus x minus 2. So this equal to 0, let it be. So we have to factorize this. So this should be, product should be minus 1 and sum should be product should be minus 2 and sum should be minus 1. Right. So that way we have to factorize it. If we do it, we end up having x minus 2 into x plus 1 is equal to 0. So my denominator factors here will be x by x minus 2 into x plus 1. So now here if you observe, this will be falling under our first case in our type 1, that is linear non-repetitive linear factors in the denominator. So if we are having this non-repetitive linear factors in the denominator, how we are going to express this? So this will be equal to a by x minus 2 plus b by x plus 1. So now here what is our second aim? To find the values of the capital alphabets A and B. So how we'll be finding capital A and B? By simplifying both the LHS and RHS of the given equation. Okay, Siddharth has already given the answer. Okay. So what about others, guys? So those who are following with me, please let me know the values of A and B. Okay, correct, Siddharth. Your answer is perfectly correct. So can you guys please let me know the values of A and B, capital A and B here? Quickly, what is the value of A and B here? So if we once got the a and b values, we can substitute and we can integrate. So let me simplify it here. So I'll just erase here. So we are having x by x minus 2 into x plus 1 after our factorization of denominator. So this will be expressed as a by x minus 2 plus b by x plus 1. So here we have to find ab values. So let's take the LCM on the RHS. So it will be x minus 2 into x plus 1. Here it will become a into x plus 1 plus b into x minus 2. And what about other side? X by x minus 2 into x plus 1. So both are same, so they will get cancelled. And what about the remaining things? Ax plus bx plus a minus 2b. So here we take x common, it will be a plus b, and the remaining will be a minus 2b. So if we compare the coefficient of x on both sides, so a plus b will be equal to 1. And here the constant we are having on the RHS, but there is no constant on the LHS of the given equation. So that means my a minus 2b will be equal to 0. Right, so I end up having two equations for a and b and 2 and b. So let's simplify it and find the values of a and b here. So here from this equation, a will be equal to 2b. So let's substitute that. So 2b plus b equal to 1. That is 3b is equal to 1, where b will be equal to 1 by 3. So if b is 1, what about a? So a equal to 1 minus b, that is 1 minus 1 by 3. So LCM 3, so 3 minus 1, it will be 2. So where the a value will be here equal to a by 2. So now we end up having our values a and b. So a is equal to 2 by 3 and b here is equal to 1 by 3. So now if we substitute, what will be our integral? So my integral now it will be, so my a value is 2 by 3. So 2 by 3 by x minus 2 plus 1 by 3 by x plus 1. So this I have to do my integration separately. So I hope you guys got this answer. So now you know how to do this separate integration. So it's as simple as that. So if you end up doing this integration, the final answer will be this one. So 1 by 3 log of x minus 2. Sorry, 1 by 3 log of 2 log of x minus 2 plus log of x plus 1. So this will be the final answer here. So I hope you guys got this one. So we can move on to the next one. Okay, most of you got it. So let's move. So let's do one more question so that you guys are familiar with this method of rational integration of rational functions. So just quickly solve this and we'll just move on to our next method. So while comparing to our previous one, this will be a bit tricky. So just try to simplify this. So as I have given a more information how to solve and all for our previous question. So this you would able to solve by yourself. So just give it a try, guys. Quickly. So initially it's in terms of x, but here in terms of x square. So now how we are going to solve this? So if you could write the simplest form, and that will be enough. So we are not going to, I'm not going to ask you for the last final step of the integration, because we already know how to do this integration by using our standard integrals, using our different methods and all. So my aim here is how you can reduce this given rational function into the simplest form so that you can easily apply our standard integrals and find the answer. So you can at least tell me by the simplest form of this. rational functions. So that will be enough. So there are some standard integrals. Using that, we can easily solve these types of integrals. So there will be formulas. I'll just give you at the end of this session. So those will be in terms of 1 by x square minus a square. So root over x square minus a square. So instead of finding again the integral for this type by our substitution method, right, so you can directly use as an identity. So that I'll be showing at the last. So that's why I don't want you to find the final answer for this question. I just want you guys to simplify it and just tell me the simplified integral. So that will be fine. I just want to know how you start solving this question. So that will be the overall idea here for giving me to solve this question. So just take 2 more minutes and then I'll just help you if you still have any doubts. So can anyone tell me what your first step, what is your first step that you have taken here? So if your first step is correct here, then it's easy to do the next follow up with the next steps. So can you guys tell me what is your first step which you have considered here? Come on, guys. Okay, factorize, correct. So what is a after factorization? So in general, how we actually do is, so in general, we are familiar with factorizing our quadratic, but here as we are having a power 4, so what we can do is, we can assume our x square to be t, so that we end up having in power 2, that is our quadratic form, so that it will be easy to factorize. So then 2x dx will be equal to dt. Then what will be our integral turns to be? So in place of x dx, I can substitute dt by 2 and 3 t square minus 18t plus 11. But here coefficient is 3, so I am just simplifying it furthermore. So t square minus 60 plus 11 by 3. So this will be our quadratic form of equation so far. That is t square minus 60 plus 11 by 3. So as we are divided by 3, it's obvious that we have to multiply. Right. So if I multiply, so here, if I multiply here, I should be multiplied here with 3. Right. So then it will be turning out to be 2 and 3. It will be 6. So I'm just pulling out the constant out. And I'll be having t square minus 6t plus 11 by 3 dt. So this is my form of a given integral in terms of quadratic form. So the next step is you will be doing the factorize. So is it easy to factorize this? That depends upon the equation. So I am going to give you another idea here. So without this factorization also we could able to solve questions by applying the formulas. So in further I'll just give you some special integrals. Those are actually give you direct identities, like if you are having 1 by x square minus a square dx integration, directly you'll be getting. So in general, if you have any this type of integration, what we are going to do, we'll just get into our substitution and then we'll see what our x substitution, and then we'll substitute here and then we'll be simplifying. So instead of doing all that particular process, we will be having a direct formula here, which actually makes even easier to solve our questions. Right, so if you guys get until this point, then that is good enough. So we'll just see. So this can be converted into this form also, because I think we won't be properly factorizing here. So you can write it in this form and you can apply the formula according to this. So don't worry, I'll just give you this set of formulas at the end of the session. Okay, so this all so that's the way of simplifying this given question. I hope you guys got the idea of how to do this. So I think you guys got my point. So I hope you're okay with that. So we'll just move ahead. So if you're having any questions, so please let me know, guys, if you have any questions. So here comes our next type. So in our first type of rational functions, what we have seen, where our denominator can be factorized. So what will be my other case here? Where my denominator cannot be factorized. Right. So if I am having a quadratic form of equation in my denominator, that is ax square plus bx plus c. So we already know that it is not necessary that every quadratic polynomial can be factorized. So there are some polynomials which we cannot actually factorize. So then how we actually solve that when we couldn't factorize the given denominator of the rational functions. So let's see. So here I am having ax square plus bx plus c. So what I'll do, I am going to take a common. Then it will be x square plus b by ax plus c by a. Yes or no? As I taken a as common. Right. So now if you observe, I am going to express as in terms of a plus b whole square. So that I will be taking x here plus b by 2a whole square. So if I have written as x plus b by 2a whole square, then x square is there. But I am not having b square plus 4a square. So I should be subtracting with b square by 4a square plus 2 into b by x. So I am already having b by 2ax. So this will be the term. And the remaining is c by a. Right. So now what I am having here, a into x plus b by 2a whole square plus, I am writing constants together, c plus a minus b square by 4a square. So what I have done here, I have taken this quadratic form of equation which cannot be factorized. I have rewritten that in this form of a whole into x plus b by 2a whole square plus c by a minus b square by 4a square. So if I could convert this into this form, right, so now what will be my integral turn out? So now my integral will be integration of dx by a into x plus b by 2a whole square, yes or no, plus c by a minus b square by 4a square. So now this is my denominator where my denominator cannot be factorized. So now in place of x plus 2a, I am going to substitute t. X plus b 2a will be equal to t. Then my dx will be equal to dt because b by 2a is nothing but a constant. Yes or no? So my dx will be equal to dt. So now my integration term will be turning out to be dx by a will be remaining as t here. X plus b to a, it will be t square. Yes or no? So here plus. So if I have assumed this to be a k, that means my c by a minus b square, my 4 square, as it's a constant, I am going to assume it to be a, k. Right? So I can substitute that here, or else we can just leave it as it is. C by a minus b square minus 4a square, as it's a constant. So as it's a constant a, I can pull out my a also. So now my integral will be turning out to be dx by t square plus. So here what I am assuming is, as I mentioned previously, we will be having formulas related to 1 by x square plus a square or 1 by x square minus a square. So those typical functions. So here I am assuming my c by a minus b square by 4a square is equal to some k square, as it's a constant. So depending upon the sign it will be coming. So plus or minus k square. So even if I didn't factorize my denominator, I can substitute in place of x plus b by 2a, I can substitute t and I can further simplify it. It's dt. What's the thing? Shyam, I didn't get you. Okay, sorry. Yeah, I got it. So here it will be dt, yeah. So in place of dx, I'll be substituting dt, okay. Right. So my aim here is, even I couldn't factorize my denominator, I can bring my quadratic expression as in the form of either x square plus a square or either in the form of x square minus a square, because we directly have our identities, so that without any further integration we can simply apply the standard integrals and we'll be finding the answer. So that's the only reason we'll follow this methodology and rewrite our given denominator of a rational function in such a way that we end up having it's in the form of 1 by x square plus a square or x square minus a square. So whatever the x, so it should be a variable, and here the other will be a constant. So it can be in place of x and a, it can be any other things, but x should be a variable. So in place of here, it should be a variable and here it should be a constant. So that's the whole thing here. Right. So this is our second type of rational functions when the denominator cannot be factorized. So here we are having one more case when our denominator cannot be factorized. Right. So here comes our second case. So this is our second case in our second type of denominator cannot be factorized. So how will we be doing this? So if you observe, we are having a numerator as px plus q and the denominator as ax square plus bx plus t. So here first thing I am going to do here is I am going to equate and express my px plus q as capital A into differentiation of my denominator. Right. Differentiation of my denominator, whatever the function will be, plus constant b. So differentiation of denominator will become 2ax plus b. That means my px plus b q will be equal to capital A into 2ax plus b plus capital B. So now using the same funda by comparing the coefficients of the both sides of the equation, we end up having our capital A and capital B values. Yes or no? So when our denominator cannot be factorized and we are having a numerator of form px plus q, then our steps to follow here is px plus q can be written as capital A into the differentiation of the denominator plus capital B. So by comparing the coefficients, our A value will be end up to be p by 2a and B will be equal to q minus pb by 2a. So these are my capital A and capital B values. So once we have our capital A and capital B values, so what will be our thing here? So in place of px plus q, we are going to substitute that. Right, so it will be A, that is p by 2a. So here A into 2ax plus b. So 2ax plus b, and the denominator will be there ax square plus bx plus c. Yes or no? So this whole integration plus b again. So what is my b? So b will be q minus pb by 2a divided by, my denominator will be as it is ax square plus bx plus c. This whole integration dx. This whole dx, and whatever the constants here, that can be pulled out. Right. So by looking at here, how we will be solving the first part? So if you observe, my numerator is nothing but differentiation of my denominator, which means my first term here is in the form of f dash x by f of x integration. So we already have the standard identity for this typical form of integral, which is nothing but directly our f of x plus c. So the integration of this part is easy. Yes or no? And we know how we'll be doing this. Just now I have shown you in our previous type, that is whether if my denominator cannot be simplified, how we'll be rewriting this. So this can be rewritten as a into x plus b by 2a whole square. So plus or minus some k, where we end up having in the form of t square plus or minus k square. That means again we will be having a standard identity. Right. So the whole thing and the whole idea here is, whatever the given function here, we are actually trying to reduce that into to get our standard forms of integrals. Because if we convert that into our standard forms of integrals, then it's one step to get the answer. Yes or no? So that's the whole funda here. So whatever we are doing here, it's always to get into our standard integrals while we are dealing with when our denominator cannot be factorized. So this is our second type of rational numbers, where we have discussed two cases for our rational functions when the denominator cannot be factorized. So let's quickly solve one question and then we'll just end up our today's session, guys. So quickly look into the question. What is the question given here? You just try and solve it. I'm not asking you to completely give me the solution of it. You just have to start with it, and what will be the simplest form of the integral. First, you just tell me that. So to get the answer of it, I'm just going to give you a formula here. If we are having 1 by x square plus a square integration dx, right? So 1 by x square plus a square dx. So the answer here will be equal to 1 by a direct integration tan inverse x by a plus constant c. So you can directly apply this formula to get the answer. So try and solve this question. So by looking at the formula here, you might have got an idea how to simplify this given denominator. I have explained you that part of writing taking a common x plus. So it's actually the complete procedure, but no need to make it that complicated because you already know by looking at the quadratic equation, you will be having an idea how can we express this in a format of x square plus a square, because in that format also at the end we are having k square plus or minus t square plus or minus k square, where our t is nothing but x square here, whatever sign plus or minus k square, k is nothing but our real number. So the same thing here, 1 by x square plus a square. Yes or no? So the overall procedure I have explained you before, so don't be confused with that. So by looking at the equation itself, you might get an idea how to simplify it easily. Okay, Siddharth have already given the answer. Correct, Siddharth? Tan inverse x minus 3 by 2. Perfectly correct. So what about others? Can at least 2 more, 3 more, can I expect 3 more answers from you? Quickly, guys. So what is our given integral? So dx by x square minus 6x plus 13. So how can we write this? Okay, Shyam got it. Okay, Shivaranjani also. Two more. Quickly, guys. Okay, Arun also done. Fine. So I'll just explain you here. So here, what is my denominator? My quadratic x square minus 6x plus 13. So if I'm going to express in terms of x square or something, so I'll be taking x square. As here I am having minus 6x, so it will be obviously minus something. So 2 into 3 here. So it will be x minus 3 obviously. So x minus 3 whole square. So what is the expansion of x minus 3 whole square? X square plus 9 minus 6x. So we already having here x square and minus 6x. So plus 9. So to eliminate plus 9, I have to add minus 9. So plus 13 is already present here. So now my integration term will be converted into x minus 3 whole square. So what is 13 minus 9? 4. So plus 4. Right. So as I mentioned, according to this formula, so according to our formula which we have seen, it should be in terms of t square plus k square. So in place of t, I am having x minus 3. Fine. And in place of k, it should be in square. So I will be rewriting this as dx by x minus 3 whole square plus 2 square. So now if you observe, it is as it is in our formula, that is 1 by x square plus a square, where x is equal to x minus 3 and a is equal to 2. So let's directly apply our formula. So 1 by a, that is 1 by 2 tan inverse x. So in place of x, we are having x minus 3 and by a. So a is nothing but 2 plus constant c. So this will be our final answer here. Right. So I hope you guys got the idea of our differentiation of rational functions. So in this differentiation of rational functions, we have seen two typical types. The first type is where we can factorize the denominator of the rational function, and the second type where we cannot rationalize the denominator of the given rational function. In these two types, in first type we have seen 4 cases. So let me just give you a quick overview of it. So in our rational functions, we have seen 2 types. So first type, factorization of denominator, and the second type, not factorization. So when we have a denominator which cannot be factorized. So in this we are having 4 types, that is we are having a non-repetitive linear factor, and the second case, repetitive linear factor, third case, non-repetitive quadratic factor, and fourth case, repetitive quadratic factors. So these are our 4 case which we have seen in our first type of rational function. In our second type, we have seen if our denominator cannot be factorized, so how we'll be simplifying it? So by rewriting that in the form of x minus b by 2a whole square. So this is our first type. And the second type, if even our numerator is having px plus q, we'll be writing our px plus q as in terms of capital A into the differentiation of the denominator, that is ax square plus bx plus c, differentiation of this plus capital B. So this is our overall recap of what we have covered in our integration of rational functions. So the next we are having our irrational functions. So that we will be looking into that topic of integration of irrational functions in our next session of our indefinite integrals. So I hope you are clear with this today's session. If you are having any questions and queries, so please let me know, guys, so that we can have a discussion and I can clarify your doubts. So that's all for today. We can just continue the rest of our concepts in our indefinite integrals in our next session of indefinite integrals. Thank you, guys.